Welcome to our presentation, Smartphone Ergonomics, Applying Lean Six Sigma Tools and Multitask Evaluation Models to Quantify Physical Exposures and Compare Solutions. I'm Murray Gibson, founder of Saturn Ergonomics. I'm a licensed PE and a CPE, and I'm an ergonomics consultant and innovator, and I'm also a PhD student at Auburn University.
Hello, everybody. I'm Ravinder Thaper. I'm an ergonomics research intern at Saturn Ergonomics, and I'm also a PhD student at Auburn University. And my focus area of research is ergonomics and safety.
In this project, I've had an interest in applying ergonomics to the modern touchscreen smartphone for some time. It's an area that I think is in its infancy, and Saturn Ergonomics has been looking at its smartphone ergonomics for several months now. And also we've recently had a collaboration with Auburn University with a industrial and systems engineering senior design team in fall of 2020, where they applied the Six Sigma and Lean DMAIC process to smartphone ergonomics. And really the beginning, I think this is from like late summer of 2018. I had an employee ask, can we apply ergonomics to the smartphone? And I said, of course you can. Wherever you have people doing physical activity or work or applying forces and postures or whatever, you can apply ergonomics. And so we went up to the dry erase board and we started just brainstorming what some of the potential problems were that we observed and experienced ourselves, potential root causes and solutions. And so this is kind of the origin. I know it's kind of messy, but this is kind of the origin of the interest in this area. This is the DMAIC process: define, measure, analyze, improve, and control. And this is a 5-step project applied by the Auburn University senior design team. And the presentation will follow this outline. The initial steps, you define your problem, what your objectives are, what you're trying to do. And then you go to measure, what are your different things you can measure, and then you begin measuring. Analysis, you analyze the problem, and also you look at your potential solutions and analyze and compare solutions. And then the final steps are improve and control.
As you all know that smartphones are becoming a vital part of everyone's life today, from students to middle-aged to finally senior citizens. The young generation is spending an extensive amount of time on the phones these days. The accessibility of internet and affordability of touchscreen smartphones is somewhat causing the increased use of phones these days. As per the data from International Telecommunication Union in 2012, the number of smartphone users all over the world has increased to 6 billion. The prolonged use of smartphones may cause musculoskeletal disorders. I think most of you have heard these issues while using the smartphones, like iPhoneitis, text-neck, texting thumb, smartphone pinky, selfie elbow. So these are all the problems that people are facing due to prolonged use of smartphones. We have tried to address the issue of ergonomics that people are facing these days. So the goal of our project is to gain a better understanding of the physical exposures of using a modern touchscreen smartphone. And we are also targeting to apply multitask ergonomics evaluation models, which is RCRA, fatigue failure, to quantify these physical exposures and determine acceptable exposure limits. And our last objective for this project is to evaluate smartphone ergonomic solution technologies. And these all come under the define phase of the DMAIC approach to address the issues of ergonomics while using the smartphones. We have noticed that only a few of the researchers have actually quantified the ergonomic issues that people are facing while using the smartphones, there is very little evidence to establish or determine the acceptable exposure limits that one should be exposed to while using the smartphones. And this comes under the major phase. We have witnessed that some of the researchers have tried to address the issues that people are facing due to the use of the prolonged use of the smartphones. And those are the problems that people are facing in the shoulder, neck, wrist, thumb, neck and shoulder pain, and MSD. And overall, people are like having the poor or non-neutral postures while using the smartphones, because the smartphone is so handy that when people want to use their phone, they keep on using their phones and they don't take care that they are in the non-neutral posture, which leads to the problem when there is a prolonged use of the phone. And this has also led to anxiety and sleep disturbance in some of the people when they use their phones. There are various causes of injuries while using the smartphones. Some of the researchers like Xiong and Muraki in 2014, they established that smaller buttons cause increased muscle activity, and the muscle activity increases while holding and using the smartphones in one hand only, which was established by Lee et al. In 2015 and Z et al. In 2016. Some of the other researchers have also noticed that there is an increased neck tilt, flexion angle, and forward shift of the head increase. Like people are facing these types of problems when they use the smartphones. So there is very little, or we can say very few people have gone or done research in this area, like what could be the possible solutions. There is one researcher, Dennerlane, in 2014 found that accessories may improve non-neutral postures like wrist and hand postures. Like if the person use thin external Bluetooth keyboard with their computer, it may possibly help in avoiding the non-neutral posture of the user.
Okay, if we look at the different levels of measurement, you could measure activity on a smartphone at the device level. You could look at hours a day, your number of sessions a day. You could look at aggregate level, the percentage of the time you use different apps, like number of texts, email counts per day, things of that nature. You could also look detailed level. For example, within your messages app, the number of texts, number of words per text, characters per word, that sort of thing. If we look at device interaction, you hold and support the device in your hand. You also have touch and gestures. Those are the physical interaction. You also have things such as voice and facial gestures, things of that nature that are more not as really classical physical ergonomics. But the things I felt we can make some headway with is holding the device and also touching the device, particularly the keyboard, the touch force, duration, and the frequency. Now, just fundamental ergonomics problem solving. We look by body part or region, we can identify risk factors, root causes, and solutions. For example, with the neck, we see a risk factor is forward neck flexion, looking down. In the root cause, low screen viewing height, and also a long use duration. For example, watching a video or reading an ebook. Solutions, you can use a stand type product, a tripod, different kinds of mounts. Instead of you looking down, get the phone up where you can see it in your line of sight. You could also display the content on a monitor or a television instead of looking at the phone. If we look at the hand wrist, gripping the phone, a lot of times we use a pinch grip. So you only have about 20% of the strength that you would in a power grip. And particularly the larger phones, the wide grip span. Then if you have a bent wrist, it reduces strength. And also we overgrip phones. They're so expensive to prevent dropping it and breaking it. So I think we apply actually more force than we need to for that security. And then there's a static grip, which results in a high duty cycle. But if we look at the root causes, lack of a handle, high cost of a phone, sometimes we need the speaker up to our ear, a large screen size that requires a wider grip, and also protective cases, particularly some of the large, bulky ones. But if we look at handle products, for example, the pop socket, lazy hands, the eye loop, things that provide a handle for you to hold on to the phone. Then, of course, the stand products help. Continuing for the hand and the wrist, repetitively typing on the touchscreen keyboard. Exposure is typically concentrated to select fingers, particularly the thumbs, or often one thumb. And as I said, the higher duty cycle, and as you in particularly if you higher frequencies, you typically have increased tap or touch force, and there's a positive correlation between touch force and duration, so that increases duty cycle. Now, if we look at solutions, so those are root causes. Looking at solutions, things to reduce the amount of typing that you do. For example, the iPhone's word suggestion bar. Partially type the word and then touch it. Use the dictation feature. You simply talk into your phone instead of typing everything. We use the technology in the phone itself. This is interesting. We look at the hand and the wrist, extended reach across the screen, the thumbs reaching across the screen. And that's particularly stressful with the larger phones. And if we look at the root causes, the large screen size, the protective cases make the phone larger and bulkier than it is. But really important is the co-contraction of muscles controlling the thumb. When we have precise controlled movements, they require significant co-contraction of the antagonist muscles. So you can't just flop your thumb over there. The other muscles that are the co-contractors are really into play when you're doing precise control like that. Now, solutions, the iPhone reachability feature, you can swipe down at the bottom and bring the screen downward so you don't have to reach up to the top. The Thumbly keyboard app, that looks pretty cool. Keeps your typing within the natural range of movement of the thumb. Now, we look at multitask analysis. We want to quantify smartphone physical exposures and determine acceptable exposure limits. I'm going to do a rapid review. If we look at duty cycle, it's basically the percentage of the time that we're applying force. Now, here are equivalent duty cycles. Now, all of these we're applying force 40% of the time. It could be 2-second forces or 4 1-second forces. Using Dr. Potvins' MAE equation, if we know duty cycle, for example, a 0.4 duty cycle, we can see that the MAE, or maximum acceptable effort, is 20%. So it's okay to use 20% of your maximum strength for 40% duty cycle. Now, how do we apply that to smartphone ergonomics? We look at the risk factor of forward neck flexion. If we look at that posture, for different degrees of neck flexion, you use the further you look down, you use a greater percentage of your maximum strength of your neck muscles. And the acceptable duty cycle decreases accordingly. Now, see how you do the calculation? We simply reconfigure the MAE equation and we solve it for duty cycle. And we use percent MVC, or maximum voluntary contraction, instead of the MAE. And we solve for those. But now the RCRA, the recommended cumulative recovery allowance, this is basically a derived model from Dr. Potvins' MAE equation. What this does, if we know the force's frequency, magnitude, and duration, we can calculate a recovery time. So typically, if we had multiple forces, different durations, different magnitudes, we would calculate a recovery time for each force. That would be add those together. That's our model recovery. Then our actual recovery is the time during the cycle when we're not applying force. And the ratio of the model recovery to the actual, and if it's less than 1, that means you have sufficient recovery for your muscles to recover and prevent the unacceptable buildup of fatigue, or unacceptable levels of fatigue. And you see the color coding system as well. Okay, this is the RCRA equation if you want to dig into a little bit deeper. Now, how can we apply that again to smartphone ergonomics? If we look at a neck flexion calculator, we can select 45 degrees forward neck flexion, enter the duty cycle or the percentage of time that we're in that posture, and we see an RCRA ratio of 1.3. That means we don't, given that posture and the percentage of maximum strength it requires, and the duty cycle, the rest that we have, we don't quite have enough recovery time. So it's a 1.3, or it's yellow, moderate. Here's the calculation if you want to go back and dig into that deeper and see how I calculated that. Okay. Now if we looked at texting and thumb forces, there's sort of a dilemma. I need a reasonable population strength for the thumb, text, or touch strength. And most of the pinch grips, I believe, are simply too high. And they have more mechanical advantage than when you're reaching across the middle of the phone texting. And I couldn't find the data, so I set out to obtain a reasonable value, and I noticed that my lateral pinch grip strength is almost identical to a published value, the average. So I'm practically myself an average strength level, and the pinch, knowing that the pinch grips correlate well with each other. An idea if I could measure my maximum thumb text or touch force, and I could use that as a reasonable value, and I could scale the male and female strength values accordingly. So I did that. I simulated the position of texting with the thumb, measured my, so came up with a mean of 8.2 and 5.4 for the female. And so we're going to use that value of 8.2 as a temporary reasonable value, actually my strength. And then the female value is almost, in the prior data, almost exactly 2/3 of the mean. So that's how I came up with those values. If we look at published values, we can see Nam and Shin, 0.13 pounds, Asakawa, 0.11 pound, and Liu, 0.18 pounds. So if you average those, 0.14 pounds. And I was looking, okay, how do I measure a thumb, text, or touch force? And there's some problems with these papers, or not problems, but I don't think there was an element of realism that translates into texting force. For example, the Asakawa paper was looking at a touch force on a tablet that was laid down flat on the table. And that doesn't really have the realism of texting. So I wanted to actually measure texting force. And I had an early fixture concepts several months ago, and you can see gradually progress there. One weekend, I decided to actually build a fixture, and I built a fixture to measure texting force, and it works reasonably well. I can set up the camera and actually see the dial, and also I could see the fingers too, and even measure the touch duration. Okay, here's the published data versus the data I measured. At relaxed speed, a touch force of 0.17 pounds, and at fast speed, a touch force of 0.31 pounds. Okay, now I wanted to use Dr. Gallagher's fatigue failure model. So if we look at, here's the basics of fatigue failure. Some definitions. US is ultimate strength. In his duet model, that's 1.4 times the maximum voluntary contraction of whatever force type you're looking at. And the theory there is that the tendon will break at 1.4 times the maximum strength you apply with that movement. Okay. If we look at N is cycles to failure, the number of cycles at a given percentage of ultimate strength for the material to fail. In our case, tendons, ligaments, that sort of thing. N is an exposure count, the number of times a shift a worker is exposed to a certain level of ultimate strength, or ultimate stress, I should say. Cumulative damage, you calculate that at each exposure level, say a percentage of your maximum strength. You would take the total count of the number of times you do that, and then divided by the cycles to failure. So if the cycles to failure were 10,000, took 10,000 cycles to fail, for that tissue to fail, and I did 50 of those, the cumulative damage for that one element would be 50 divided by 10,000. So you simply divide those up and you get your cumulative damage. This, you can see the ultimate stress versus cycles to failure. At high levels of ultimate stress, the tissue fails with very few cycles, 10 cycles, 100 cycles. At very low percentages of ultimate stress, you can see it gets into the thousands. So if it's a very low force, your body can tolerate a lot of repetition without damage. But if it's higher forces, it's a nonlinear relationship, and the damage increases. So Dr. Gallagher's models factor that in, and it's really cool. Here's the table 1 of the duet model, distal upper extremity tool. And you can see the OmniRes scale, subjective rating scale, and it shows the estimated cycles to failure, and then the damage per cycle weighting. And here's an example of how, if you want to see an example of doing that calculation, of calculating cumulative damage, I have it in the table here at different percentages of ultimate stress in the number of cycles. Say we did 500 of these at 40%, we did 75 of 50%, 12 of 60%. We simply add those up. You divide your cycles by the cycles to failure, and you get your cumulative damage. And what you do with that number is you can see the CD, you plug that in, you get the Y prime, and you plug that in to get a probability of an outcome, which is an injury plus pain the last year, they have Auburn University has a epidemiology database that has around 1,000 jobs. And so that's how that came about. But the probability of injury, somebody reported pain or they had an injury over the last year, given that probability level. Okay. The fatigue failure application, evaluate texting. I thought this was really cool, but I made some assumptions. Texting style is holding the phone in one hand and texting with one thumb. Thumb text force is average male strength or female strength, those values that I arrived upon by measuring my strength and scaling it for the female. Texting speed is 36 words per minute. That's sort of a common, sort of like typing on a computer. That's a common rate. And I assume the text to reading ratio is 70-30. You read faster than you text, so you probably spend, it's assumption, 70% of the time texting, 30% of the time reading. And then an average of 5 letters per word plus 1 space between words. Okay. Well, here's how that kind of calculation, or how this analysis works out. Okay. So texting style, one hand, one thumb. And let's do it for females. And we enter 3.5 hours of texting, the total number of hours per day that you text, and we can enter up to as many as you want there, as many as you can stand. And then we get an injury probability of 0.29. That's yellow. And I believe I set this one to where it was 0.2. It turned from green to yellow. I'm sorry, 0.25. It turned from green to yellow. And then 0.5, it turned red. But anyway, it gives you a way to assess the quantitatively assess texting exposure based on hours texting. I used the relaxed texting force. I didn't use, when I collected the data, I had one value that I had collected for fast texting, and it was almost double the force level. So you could have an option here, relax pace or fast texting speed. But anyway, that's how you can apply the fatigue failure model to texting. Okay. Evaluating and comparing solutions. You want to identify solutions. We identified 23 solutions, and this is a neat way by body part. I listed the solutions and I rated them low, moderate, and high benefit. So if somebody has, say, trouble with the shoulder, you could look at the solutions and see which ones will be potentially good for the shoulder. Here's a little bit more nuanced way. I want to do more this kind of analysis for solutions. For example, that flexible mount, you can see it really improves the neck, but the problem there, if you have to reach for the phone, you reach up and touch it, then it's going to put some stress on your shoulder. So we need some kind of way to quantify. And I may do it with a pluses and minus system. But for example, the one at the bottom, elevate the phone with the arms. Okay, it really helps the neck. But then when you do that, you put the strain on the shoulder. So we need some way to reflect the negative impact on another body part. But anyway, we have a cost and then comment so you can better understand it. But anyway, these are ways to communicate solutions so people have a better idea of what solutions are out there and what might might help their situation.